Okay, today we will be discussing about Rodrigues formula for the Hermite polynomials. So we have seen about the generating function of Hermite polynomial in the last lecture. So the generating function for the Hermite polynomial is given by exponential 2xz minus z square equal to summation over n is equal to 0 to infinity hn of x divided by n factorial into z raised to n. So now we will be expanding the right hand side, putting n is equal to 0, 1, 2, 3, etc. So this will give you h0x divided by 0 factorial z raised to 0 plus etc. plus the nth term will be hn of x by n factorial z raised to n plus the higher order terms. Okay, so next step is we are going to differentiate the above expression with respect to z n times using the Leibniz theorem, and then we will be putting the value of z equal to 0. So that means differentiating this expression n times with respect to z and put z equal to 0. So the differentiation will be dou n by dou z raised to n, the exponential term, equal to, now we are differentiating this one, so we can see that each term will go to 0 n times we are differentiating with respect to z. All terms before z raised to n will be cancelled out. Okay, so the nth term will give you n into, first differential will give n into z raised to n minus 1, so second differential will give n into n minus 1 z raised to n minus 2, and I continue, and it will continue. So though finally you will get n into n minus 1, n minus 2, etc. up to 1 into hn of x divided by n factorial z raised to n minus n, plus higher order terms will be 0 because we are putting z equal to 0. There will be this power of this term will be z raised to 0, and the next power will be z to the power 1, 2, etc. So when we put z equal to 0, all higher order terms will be equal to 0. So when we solve this one, n factorial, this n factorial will go, so what is left out is hn of x. So the expression become hn of x equal to dou n by dou z raised to n 2xz minus z square. Okay, now you can write the exponential part. We will just trying to modify the exponential part, that is z minus x whole square will be a minus b whole square term, will be x square plus z square minus 2xz. So now I'm going to do x square minus this term, so this will be x square minus of this term. You will get the exponential part of the generating function, that is 2xz minus z square. So that means your generating function you can modify it as exponential 2xz minus z square equal to e raised to x square minus z minus x whole square, that is e raised to x square into exponential minus of z minus x whole square. So the function can be written as hn of x equal to dou n by dou z raised to n e raised to x square into e raised to z minus of z minus x whole square. Since the differentiation is with respect to z, we will take x square outside of the differentiation, so e raised to x square into dou n by dou z raised to n exponential minus of z minus x the whole square. Okay, so now in this expression what I am trying to do is put this term z minus x equal to 2 t. So that is substituting z minus x equal to t. So now the previous differentiation is with respect to z. Okay, so here I am going to differentiate this expression with respect to z. So dou by dou z, so this dou by dou z, because x is a constant, because our differentiation is with respect to z only, so dou by dou x equal to dou by dou t, that is you can write it like this: dou by dou z equal to dou by dou t into dou t by dou z, dou by dou t into dou by dou z of t is equal to z minus x. So this will give 1, so dou by dou t, because we are taking x is independent of z. Okay, so your function dou n by dou z raised to n exponential minus of z minus x whole square equal to dou by dou t and z equal to, dou by dou z is equal to dou by dou t, so dou by dou n by dou t raised to n exponential minus of t square. Okay, Now, since we have putting a limit z equal to 0, then from this expression when z equal to 0, t will be equal to minus of x. So z equal to 0, t is equal to minus x, to t equal to minus x. So dou by dou t n is equal to x into dou by dou t n of exponential minus t square at t is equal to minus x can be written as like this. This can be proved by successive differentiation. For example, if you take this equation, the first differential of dou by dou t of e raised to minus t square at t is equal to minus x equal to dou by minus, put t is equal to minus x, so this is equal to dou by dou x of exponential minus x square. Okay, so that means you can write it as dou by dou t of e raised to minus t square can be dou by dou x of dou x by dou t. So this dou x by dou t will be t is equal to minus x or x equal to minus t. This is equal to minus. This will give you minus 1. So minus dou by dou x of e raised to minus x square. T will be equal to minus x. Okay, square. So and if you do one more differentiation with respect to t, you will get, you can just try this. You will get minus 1 whole square into dou square by dou x square e raised to minus x square. So if you continue for n times, your expression will become minus 1 to the power n dou by dou x raised to n e raised to minus x square. So from the previous expression, hn of x equal to e raised to x square into, that is this expression become hn of x equal to, this expression can be written as hn of x into minus 1 to the power dou x raised to, sorry, this one, hn of x equal to e raised to x square into minus 1 to the power n into dou n by dou x raised to n e raised to minus x square. So hn x equal to minus 1 to the power e raised to x square dou n by dou x raised to n e raised to minus x square. This equation is called the Rodrigues formula for the Hermite polynomials. Okay, so if you substitute each values for n is equal to 0, you will get h0 of x equal to, put n is equal to 0 minus 1 to the power 0 e raised to x square dou n is equal to 0, so this is equal to, this will go, that means e raised to minus x square, dash x square, that will give 1. So h0 of x will be 1. Put n is equal to 1, you will get minus 1 to the power 1 e raised to x square dou by dou x of e raised to minus x square. This differential will give you e raised to minus x square into minus 2x. So on solving you will get 2x. Similarly, if you put n is equal to 2, you can just try this one, you will get the h2 of x equal to 4x square minus 2. So that means by using the Rodrigues formula, you can generate Hermite polynomials of different orders. Okay, now next we will move over to the orthogonal property of Hermite polynomials. So the orthogonal property of Hermite polynomial is defined as integral minus infinity to plus infinity e raised to minus x square hn of x into hm of x dx equal to 2 to the power n factorial root pi delta mn, where delta mn is our Kronecker delta. That value of delta mn will be equal to 1 if m is equal to n, and that will be 0 if m not equal to 0. Okay, so now we will try to prove the orthogonal property of Hermite polynomials. Okay, so we will start from the generating function once again to xz exponential to xz minus z square. This, like in the case of the Rodrigues formula, we are trying to modify this raised to x square minus x square minus z minus x all square. Now you will get two different equations corresponding to n and m, two different orders. E raised to x square is, put z equal to z1. Z1 will give z1 minus x all square into summation over n is equal to 0 to infinity hn of x n factorial x raised to z1 raised to n. Then corresponding to m, e raised to x square z2 minus x all square summation over m of x m factorial z2 raised to m. So these are two different equations. So you multiply equation 1 and 2, this become e raised to x square z1 minus x all square into e raised to x square, this time equal to summation over two variables n hn of x into hm of x divided by n factorial m factorial z1 to the power n and z2 to the power m. Okay, so next step we will be multiplying both sides with exponential minus x square and integrating between the limits minus infinity to plus infinity. So we are multiplying these two both sides of the equation with e raised to minus x square and then integrating between the limits. So the summation over mn minus infinity plus infinity e raised to x square e raised to minus x square hn of x hm of x z1 to the power n z2 to the power m factorial dx equal to minus infinity to plus infinity e raised to minus x square into x square minus z1 minus x whole square into exponential x square minus z2 minus x whole square into dx. Okay, so this is e raised to minus x square, then you will combine these two, x square plus x square will give 2x square minus of z1 minus x square minus z2 minus x whole square dx. So combine these two, minus x square, there are 2 plus 2x square, this will give you x square minus of a minus b whole square. So if expand these two terms, you will get z1 square minus 2z1x plus x square minus of z2 square minus 2x z2 plus x square. Okay, so since the integration is with respect to x, all the z terms will come out of the integration, that will exponential minus of z1 square plus z2 square will come out of the integration, then the remaining term is this one. Okay, so in this expression you take minus x square plus 2x into z1 plus z2. You can this x square and this x square will combine together, will give e raised to minus x square plus 2x will be taken as common and this will give z1 plus z2 dx. Okay, so now we have a standard integral minus infinity plus infinity e raised to minus ax square plus 2bx dx equal to root pi by a e raised to b square by a. Integral minus infinity plus infinity exponential minus ax square plus 2bx dx equal to root of pi by a into exponential b square by a. So when we compare this with this, this integral with the standard integral, you can find out that here a is equal to 1, here 2b is equal to, this 2b is equal to 2 into z1 plus z2, which means b is equal to z1 plus z2. So the integral will be reduced to square root of pi by 1, where a is equal to 1, root of pi into exponential z1 plus z2 square, a is equal to 1. So this equation will reduce to summation over m n minus infinity plus infinity raised to x square, left hand side, the right hand side become exponential minus z1 plus minus of z1 square plus z2 square into root pi into root of exponential this time. Okay, so root pi into just comparing this to minus z1 square minus z square plus z1 square plus z2 square, 2 z1 z2, so this 2 will go, what is left out is e raised to 2 z1 plus z1 into z2. So expanding the exponential e raised to x in the form of e raised to x, so this become root pi into 1 plus x square by 2 factorial plus x cube by 3 factorial plus etc. Here x will be your 2 z1 z2. So this is your expression. So in general, root pi into summation over n 2 z1 z2 to the power n summation over n 2 z1 z2 to the power n divided by n factorial. So this I will modify it as root pi into summation over n 2 raised to n z1 to the power n z2 to the power n divided by n factorial. Now you can write z2 to the power n can be written as equal to z2 to the power n is equal to z2 to the power m delta mn. That means when m is equal to n, z2 to the power n is equal to z1 z2 to the power m. Okay, so in order to incorporate the Kronecker delta, I'm just modifying this z2 to the power n as z2 to the power m delta mn. Okay, so z2 to the power n is here, so this z2 power n is just modified as z2 to the power m delta mn. Okay, that is the only change. So the left hand side remains same, so square root of pi summation over mn 2 to the power n z1 to the power n z2 to the power m delta mn divided by n factorial. So one n factorial on both sides, this n factorial and this n factorial will go. Now equating the coefficient of z1 to the power n and z2 to the power m on both sides. So the left hand side become minus infinity to plus infinity e raised to minus x square hn of x hm of x divided by n factorial m factorial delta x root pi 2 to the power n divided by n factorial delta mn. So here also here n factorial will go, no problem whether it is going this type or this type, doesn't matter. So n factorial will cancel out, so what is left out is integral minus infinity plus infinity e raised to minus x square hn of x hm of x dx equal to root pi, this m factorial come to the right hand side, root pi 2 raised to n m factorial delta m. Okay, so we know that if m is equal to n, delta mn is equal to 1. Okay, and delta mn is equal to 0 if m not equal to n, which means integral minus infinity plus infinity e raised to minus x square hn of x hm of x dx equal to root pi 2 raised to n factorial if m is equal to n, and this is equal to 0 if m not equal to n. So in general you can write as integral minus infinity to plus infinity e raised to minus x square hn of x hm of x dx equal to root pi 2 raised to n factorial delta mn. So this is your orthogonal property of Hermite polynomial. Okay, thank you.